You know, usually when we look at a post-op x-ray, say a complex tibia fracture that's just been fixed, there's this profound expectation of permanence.
Oh, absolutely. Right.
Right, like it looks like architecture. You see that solid titanium plate spanning the bone. You see those perfectly placed bicortical screws, and it just looks completely unmoving. It looks clean, static, and, well, totally resolved.
Right. It feels like looking at a finished bridge.
Yeah.
Like the scaffolding is down, the job is done, and you just expect it to sit there peacefully.
But then you zoom in, like if you were to zoom down to the microscopic level, right into the crystalline lattice of those metallic materials and into the cellular matrix of the bone itself, you'd realize that solid, unmoving bridge is actually, I mean, it's a war zone.
That is the perfect way to describe it. It's the absolute definition of a constant invisible battle. You have these colossal forces, stress, strain, fatigue, just constantly assaulting the structure.
Wow, yeah.
What looks perfectly still on the screen in the clinic is actually a highly volatile, dynamic environment. Physics is actively testing every single millimeter of that implant and every single living cell of that bone 24 hours a day, with every single heartbeat and every single footstep.
And understanding the rules of engagement in that invisible battle is exactly why we are here today. Welcome to this deep dive into the foundational principles of biomechanics and structural mechanics.
Let's dive right into it.
So if you are joining us, your mission is very clear. You are a doctor gearing up for the FRCS trauma and orthopedics exam. And let's be entirely honest here, biomechanics can seem incredibly intimidating.
Oh, for sure.
For a lot of us, it feels like a heavy engineering degree got dropped, like completely unannounced right into the middle of our surgical training. But our goal today is to provide high-yield revision. We're distilling this core science into actionable, memorable insights. We are basically going to take the fear entirely out of the physics.
Exactly. And, the best way to completely remove that fear is to realize that this entire field, this massive, intimidating syllabus topic, essentially hinges on just two master keys.
Two keys, okay.
Yeah, just two. If you can grasp these two keys, the exam questions suddenly stop being mysterious and they become, well, very predictable.
That's what we like to hear.
Right. So the first key is learning how to visualize and read one specific graph. And the second key is understanding a fundamental law of structural mechanics, which is simply that shape beats material.
One graph and the rule that shape beats material. I love that framework. Okay, before we jump into that war zone, let's set the stage for you, the listener. We know exactly how you are likely consuming this deep dive.
Definitely on the go.
Exactly. You are probably driving home from a long shift at the hospital, or maybe you are doing chores, or you're at the gym. You are on the move, and you cannot pull out a notebook. We know that. So we are making a solemn promise to you right now. Every crucial formula, every number, every ranked list, and every key exam discriminator is going to be stated twice.
Yes. We will deliberately ensure the most critical, highly testable points are repeated in our conversation so that you just do not need a pen and paper.
No notes required.
Exactly. We are going to build this directly into your memory through clear explanation, real clinical context, and deliberate repetition.
Okay, let's unpack this. Before we look at how whole implants and whole bones act as large structures, we have to understand how the raw materials themselves behave when they are put under force.
Right, the raw material.
And to do that, we need to visualize what is arguably the most important graph in all of orthopedics.
It truly is the Rosetta Stone for this topic. If you master this one graph, it answers about half of the questions in the entire biomechanics section. We're talking about the stress-strain curve.
The stress-strain curve.
Yeah. If you can picture this curve in your mind's eye, and if you understand what it means as you read it from left to right, you are, like, most of the way home.
Since you're likely driving, we obviously aren't going to ask you to look at a screen. We are going to verbally paint this stress-strain curve for you, line by line. And we'll explain the why behind every single bend in that line. So let's start with the axis.
Okay. Imagine a blank piece of graph paper. Along the bottom, the horizontal axis, the x-axis, is strain.
Strain.
Yeah. Strain is simply a measure of how much the material stretches or deforms when you pull on it. Up the side, the vertical axis, the axis, is stress. Stress is the actual force per unit area that you are applying to that material.
Okay, so just to lock those in for you listening. The bottom axis, the x-axis, is strain, which means how much the material stretches. The bottom axis, the x-axis, is strain, which means how much the material stretches. The side axis, the y-axis, is stress, which is the force per area applied. The side axis, the y-axis is stress, which is the force per area applied.
Perfect. Now imagine a specialized laboratory machine, a tensile testing machine. You clamp a solid piece of metal into it, and the machine starts pulling the metal apart.
Okay, so we're stretching it.
You are applying stress, and the material responds by stretching, which is strain. As the machine pulls, a pen begins to trace a line on our blank graph, starting right from the bottom left corner at 0 and moving outwards and upwards.
So we're pulling the metal, and the line starts drawing. What does that first section of the line look like?
The initial part of this line is a perfectly straight, steep climb upwards.
Like a ramp.
Exactly like a steep ramp. This straight diagonal line represents the elastic region. In this region, the deformation is completely 100% reversible.
Reversible. Okay.
Yeah. If you tell the machine to let go of the material, if you completely remove the stress, the material springs right back to its exact original shape.
Oh, like a rubber band.
Exactly like a rubber band. At the atomic level, you are literally just stretching the electromagnetic bonds between the atoms. You aren't breaking them. So when you let go, those atoms snap right back to their comfortable resting distance. That is the elastic region.
And the steepness of that straight climbing line is critical, isn't it? Because there is a highly tested name for the slope of that specific line.
There absolutely is. The slope of that straight elastic line is called Young's modulus, also known as the modulus of elasticity. And here is the single most important translation you can make. Young's modulus means stiffness.
Let me push on that for a second. Why does slope equal stiffness? Like, walk me through the actual mechanics of that.
Think about the axis we just painted. A very steep slope means the line is rocketing straight up the y-axis, the stress axis, but it's barely moving across the horizontal x-axis, the strain axis.
Ah, I see. So you have to apply a massive amount of force, really high stress, just to get a tiny little bit of stretch or low strain.
Exactly. The material is fiercely resisting your attempt to deform it. Therefore, a steeper line means a higher Young's modulus, which mathematically translates to a stiffer material. If the line is shallow, it means a little bit of stress gives you a ton of stretch, meaning it's highly flexible or less stiff.
That makes perfect sense. I am going to make sure that is permanently locked in for you listeners. Young's modulus is the slope of the elastic region, and it means stiffness. A steeper line equals a higher modulus, which means a stiffer material. Young's modulus is the slope of the elastic region, and it means stiffness. A steeper line equals a higher modulus, which means a stiffer material.
Beautifully done.
Okay, so our machine is pulling the material, the line is climbing straight up in the elastic region, and we know if we hit stop, the metal springs back. But we don't hit stop, we just keep pulling. What happens next?
Eventually, that straight line hits a ceiling. The atoms can't stretch any further without fundamentally changing their relationship to one another. The line reaches a very specific milestone called the yield point.
The yield point.
Yes, the yield point is the exact moment where the material stops springing back. It marks the absolute end of the elastic region. Once you pull past that yield point, you have crossed a threshold and entered the plastic region.
And plastic, in this mechanical engineering sense, means permanent.
Precisely. In the plastic region, the deformation is permanent. If you tell the machine to let go now, the material will not return to its original shape. It has been permanently altered.
Because things are shifting inside.
Right. At a molecular level, the planes of atoms are actually sliding past one another into entirely new positions. It's a process we call slip. On our graph, after it hits a yield point, the line stops climbing so steeply. It curves over and begins to climb much more gently as it stretches out sideways in the plastic region.
So it is stretching, it is permanently deforming, but the metal hasn't physically broken in two yet. It is still taking on more stress, just at a different, slower rate.
Correct. The line continues to climb, albeit more gently, until it reaches the absolute highest peak of the entire curve. That peak altitude is the ultimate tensile strength, commonly abbreviated as the UTS.
The ultimate tensile strength, the absolute peak of the mountain.
Yes. The UTS is the absolute maximum stress the material can possibly take before it fails. It is the ceiling of its strength. Once you pass that peak, the line actually dips down a little bit as the material violently narrows, a phenomenon called necking, and then the line simply ends. That end point is fracture. The material breaks in two.
Okay, so just to recap the visual journey of the line. We start with the elastic region, which is straight, steep, and completely reversible. Then we hit the yield point. We cross over into the plastic region, which is curved, flatter, and permanent. Then we climb to the very peak, which is the ultimate tensile strength. And finally, the line drops slightly and terminates at failure.
That is the complete life cycle of a material under tension. But here is where it gets highly testable on the exam. Different materials trace radically different versions of this curve.
How so?
Well, by looking at the shape of the curve, and specifically how much of that plastic region exists, we can categorize materials into two major personalities: ductile and brittle.
Let's break those down. Let's start with ductile.
A ductile material, like most of the metal alloys we use in orthopedic surgery, undergoes a massive amount of permanent plastic deformation before it finally fails.
Hmm.
On our graph, its plastic region is very long and stretches far to the right.
Ah, okay.
Yeah, the material bends, it stretches, it necks down. It gives you a tremendous amount of physical warning before it finally gives up and breaks.
So a ductile material is something like a blacksmith forging a hot piece of iron. You hit it with a hammer, and it dents, it bends, it morphs, but it stays in one piece.
The atomic lattice has the ability to slide around without shattering.
Yes, exactly. The metallic bonds between the atoms allow for those slip planes to move. Now, contrast that with a brittle material. Brittle materials, like ceramics or PMMA bone cement, have almost zero plastic region whatsoever.
Zero plastic region. So what does their line look like?
On the graph, the line for brittle material climbs incredibly steeply in the elastic region, meaning it has a very high Young's modulus and is incredibly stiff. But then, as soon as it hits its yield point, it almost immediately ends. It just snaps.
Yeah, there is no long, curved plastic region stretching to the right.
So a brittle material is like a porcelain vase. It is incredibly stiff, it doesn't bend at all, but the second you exceed its strength, it shatters violently. There's no warning, no bending, it just fails.
Exactly. Because ceramics use ionic bonds rather than metallic bonds, the atoms are locked in rigidly. They cannot slide past one another. So, to summarize, ductile materials deform a lot before failing. Brittle materials snap with little to no warning because they lack a plastic region.
Okay, now I want to ask for a foolproof way to separate two terms that absolutely plague candidates on the FRCS exam. I'm talking about the area under the curve terms, specifically resilience versus toughness. I will fully admit, if I'm reading an exam question fast, my brain tangles these two up. How do we keep them permanently straight?
It is a classic exam trap, but it becomes trivial once you hold that graph in your mind. Both resilience and toughness refer to energy. And mathematically, on a stress-strain graph, energy is represented by the physical area underneath the line. The only difference is which specific part of the area you are measuring.
Let's take resilience first.
Resilience is the area under the elastic part of the curve only, just that first straight triangle. It represents the elastic energy that the material can safely store up and then give back exactly like a spring.
So it's just the area under the elastic part.
Right. Now, toughness is the area under the whole curve, the entire thing, from zero all the way to the fracture point. Toughness is the total massive amount of energy a material can absorb through both bouncing back elastically and deforming plastically before it finally breaks in half.
Oh, I see a great mnemonic there. Toughness is total. The T's match. Toughness is the total area, meaning it's the total energy absorbed before fracture. If you think about car safety, resilience is the spring in the bumper bouncing back when you tap a wall at 2 miles an hour. Toughness is the entire front crumple zone of the car systematically crushing and permanently deforming to absorb the total energy of a highway crash so you survive.
That is a phenomenal analogy. The crumple zone is purely exploiting the toughness of ductile metals.
I'm going to state these definitions twice for you listening because this is prime exam fodder. Resilience is the area under the elastic part only, representing stored energy. Toughness is the area under the whole curve, representing total energy absorbed before fracture. Resilience is the area under the elastic part only, representing stored energy. Toughness is the area under the whole curve, representing total energy absorbed before fracture.
Perfect.
So when we pull back from all this detail, what is the core takeaway? If you only remember one thing from this entire segment on the master graph, make it this. Young's modulus is the slope of the elastic region and means stiffness, and toughness is the total area under the entire curve.
That captures the absolute essence of the graph.
But here is where we have to shift our perspective. Because as clean and elegant as that laboratory stress-strain curve is, we know the human body doesn't work like a sterile tensile testing machine. An implant in the human body rarely faces one massive, slow, continuous pull until it yields and breaks. In reality, implants face thousands or millions of tiny, repetitive steps, and that introduces a completely different, much more insidious mechanism of destruction into our war zone.
Yes, definitely. We are moving away from the physics of a single massive trauma like a car crash, and we are looking at the silent killer of orthopedic implants.
Let's talk about fatigue.
When we looked at the curve, we established that a material fails catastrophically when the stress reaches the ultimate tensile strength, the UTS. That makes logical sense. But in the real world of orthopedics, materials routinely and predictably fail at stresses that are well below their ultimate tensile strength.
Wait, hold on. If the UTS is the defined peak strength of the material, how does it break if you don't actually reach the peak?
Because of the relentless nature of time and repetition. Fatigue failure is strictly defined as failure under repeated cyclic loading at a stress level that is well below the ultimate tensile strength.
So it's not the sheer size of the load, it's the cyclic repetition of it. I know the classic textbook analogy is bending a paperclip, right?
Yes, the paperclip is the perfect miniature demonstration of fatigue. If you take a metal paperclip and you bend it up once, you haven't broken it. You haven't come close to exceeding its ultimate tensile strength on that single bend. But if you bend it up and down 20 or 30 times, eventually it snaps in your fingers.
Right, the force didn't change.
The actual force your fingers applied never increased. You never reached the UTS. But the cyclic loading caused microscopic cracks to form at the surface, propagate inward, and eventually cause fatigue failure.
And structurally, that is exactly what happened to early hip implants, wasn't it? The early engineers looked at the UTS of stainless steel and thought, well, the forces of walking are way below the UTS, so this implant will last forever.
Exactly.
But they didn't account for fatigue. Every time a patient took a step, they were applying a load. A single step is nowhere near enough to snap a metal stem, but 2 million steps a year. That cyclic loading created micro cracks that eventually caused the stems to snap right in half inside the patient.
Exactly. It's a hard-learned lesson from early joint replacement history. Fatigue is the enemy of any load-bearing implant.
But surely there is a safe zone. We put millions of implants into patients today, and they don't all just break eventually. Is there a level of stress that is so microscopically low you can cycle it forever without it breaking?
Yes. And that brings us to the crucial concept of the endurance limit, which you will also see written as the fatigue limit.
The endurance limit. What is the strict definition for the exam?
The endurance limit is the specific stress threshold below which the material will never fail, regardless of how many millions or billions of cycles it goes through. If the stress applied during cyclic loading stays completely below the endurance limit, the material theoretically has an infinite fatigue life.
Infinite. So under the limit, the material is safe forever. Above the limit, failure is just a ticking countdown of cycles.
Exactly. If the cyclic stress is above the endurance limit, even if it is still way below the ultimate tensile strength, it is only a matter of time and cycles before a microscopic crack turns into a catastrophic fracture.
Now, I know examiners love to set traps around this concept of the endurance limit. What is the classic trick question they will throw at a candidate?
The trap is trying to make you believe that the endurance limit is a fundamental, unchangeable property of the raw element itself, like its atomic weight or its melting point. It is absolutely not. The manufacturing process directly and radically alters the endurance limit.
Really? So a block of titanium can have a different endurance limit depending on how it's treated in the factory?
Precisely. How you forge the metal, how you heat treat it, and especially how you polish the surface, all matter. Fatigue cracks almost universally start at microscopic surface defects. A tiny scratch, a pore, a machining groove.
Ah, I see.
Therefore, a highly polished, mirror-finish implant has a significantly higher endurance limit than a rough or scratched implant, even if they are milled from the exact same block of titanium. Furthermore, if the manufacturer introduces surface compression treatments, like shot peening, it compresses the surface atoms, making it incredibly hard for a crack to even open up. This artificially raises the endurance limit. It is a manufactured property, not a universal constant.
That is a phenomenal point. So when we are careful not to scratch a plate or a rod in the OR with our instruments, we aren't just being neat. We are actively protecting the implant's endurance limit and preventing a future fatigue failure.
That is exactly right. You scratch the implant, you lower the endurance limit, you invite fatigue.
Okay, let's lock this in. If you only remember one thing from this topic, fatigue is failure from cyclic loading below the ultimate tensile strength. And the endurance limit is the safe stress zone where fatigue never happens.
Perfectly stated.
Before we move from these predictable raw materials to how biological living tissues behave, I need to make sure these core definitions are hard-coded into our short-term memory. Listeners, we promised you deliberate repetition while you are on the move. Let's do a quick lock-in of these concepts, our first mid-episode recap.
I am ready. Let's do it.
Let's fire through them. What is the slope of the elastic region?
The slope of the elastic region is Young's modulus, and it signifies stiffness.
Stating that twice for the road, Young's modulus is the slope of the elastic region, and it means stiffness. Young's modulus is the slope of the elastic region, and it means stiffness. Next up, define resilience versus toughness.
Resilience is the area under the elastic part only. Toughness is the area under the whole curve.
Stating it twice. Resilience is the elastic area, toughness is the total area, toughness is the total area. Next, define fatigue.
Fatigue is failure from repeated cyclic loading at a stress well below the ultimate tensile strength.
Stating it twice. Fatigue fails below the UTS. Fatigue fails below the UTS. And finally, what is the endurance limit?
The endurance limit is the stress threshold below which a material will never fail by fatigue.
Excellent. Core concepts banked. Now, let's pivot. So far, we have been talking almost exclusively about metals and ceramics. And from a physics perspective, these materials are wonderfully predictable. A piece of stainless steel behaves the exact same way whether you pull on it fast or slow, whether you pull on it for 1 second or for 1 straight hour. But the operating room isn't a metal shop. We are attaching these metals to living tissue.
Right. And living tissue, bone, tendon, ligament, cartilage is fundamentally different. Mechanically speaking, biological materials are viscoelastic.
Viscoelastic, this is a massive topic. What does it actually mean?
Viscoelasticity is the concept that a material's physical behavior changes based on time and based on the speed or the rate of loading. It isn't a static, predictable spring like a metal wire. It has both fluid properties, which is the viscous part, and solid properties, which is the elastic part.
Time and speed change everything. Now, viscoelasticity is endlessly tested, and unfortunately, the vocabulary here is constantly muddled by candidates. There are 4 key terms we need to define with absolute precision. Let's start with the first one, creep.
Creep is what happens when you apply a constant unchanging load to a viscoelastic material, and that constant load leads to an increasing deformation over time.
Constant load, but increasing deformation.
Yes. The physical force you are applying stays exactly the same, but the material just keeps stretching and stretching as the hours and days tick by.
I want to pause you right there because I want to make absolutely sure the listener doesn't mix up creep and the next term, which is stress relaxation. Let's define stress relaxation first, and then I want to ask for detailed clinical examples to separate them in our minds forever. What is stress relaxation?
Stress relaxation is essentially the mirror image of creep. In stress relaxation, you stretch a material to a constant length and you hold it exactly there. Over time, the stress or the internal tension inside the material slowly falls away.
Okay, constant length, falling stress.
Exactly. You physically clamp it at a fixed length, and the tissue just internally relaxes, requiring less and less force from you to hold it at that fixed length.
Okay, let's apply this to the real world. Give me a vivid clinical example of creep in orthopedics.
The absolute classic clinical application of creep is applying a Ponseti cast for an infant with a club foot. Think about what you're doing. You manipulate the foot, and you apply a plaster cast that places a constant, gentle load against the abnormally tight medial tissues of the foot.
Okay, that makes sense.
The cast is rigid. You do not actively increase the load once it's on. But over the course of a week, because those infant ligaments are highly viscoelastic, they undergo creep. The fluid inside the tissue slowly weeps out, the collagen fibers microscopically slide, and the tissue slowly lengthens, increasing deformation under a constant load.
Constant load, growing strain. That is creep.
Another great example is an ACL reconstruction. You put a nice tight graft in, but over 6 months, under the constant repetitive load of body weight and muscle tone, that graft can slowly stretch out. It creeps. Even non-biological polymers do this. A polyethylene liner in a hip replacement can slowly deform or cold flow under the constant load of the metal femoral head.
Okay, so Ponseti casting and ACL stretching are creep. Now give me the clinical picture for stress relaxation.
For stress relaxation, imagine you are in the OR doing a flexor tendon repair in the hand, and the tendon ends are retracted and tight. You grab the proximal stump with your forceps, you pull the tendon to a very specific length so it meets the distal stump, and you hold it exactly there while your assistant preps the suture. Constant length.
So you're just holding it still.
Right. At first, you really have to pull hard. There's a lot of tension in your hand. But as you hold it motionless at that fixed length, you will literally feel the tension drop away. The tendon is internally relaxing. The stress is falling. That is stress relaxation.
That paints a perfect picture. Creep is the Ponseti cast continuously stretching tissue under a constant load. Stress relaxation is holding a tight tendon at a constant length and feeling the tension literally fade from your forceps. Okay, what is the third key term for viscoelasticity?
The third term is hysteresis.
Hysteresis. That sounds like a pure physics term. What does it mean for us?
Hysteresis describes the energy that is lost, specifically, energy that is dissipated as heat during a full cycle of loading and unloading a tissue.
Let's unpack this visually. We are back to drawing lines on a graph.
Yes. If you load a piece of steel, a perfectly elastic material, the line goes up a steep path, and when you let go, it comes down on the exact same path. Zero energy is lost. But if you load a viscoelastic material like a thick ligament, the line goes up one path, then when you unload it, the tissue doesn't snap back instantly. The fluid has to rush back in, so the line comes down a different, much lower path. The loading curve and the unloading curve do not overlap.
They form a loop.
Exactly. They trace a wide loop. And the physical area inside that loop represents the mechanical energy that was lost during the cycle, lost into the surrounding tissue as heat. Hysteresis is the energy lost in that loading-unloading loop.
Energy lost as heat. This actually makes total sense. If you take a thick rubber band or even a piece of biological tissue and you repeatedly stretch it as fast as you can, it actually feels physically warm to the touch. That heat is hysteresis. It's the internal friction of the fluid and the polymer chains sliding past one another. Okay, the fourth and final term, the toe region.
The toe region is a very specific, highly recognizable feature seen on the stress-strain curve of tendons and ligaments. If you look at the very start of the stretch curve, down near zero, the line isn't steep. It doesn't shoot up. It's actually a flat, gently curving horizontal bit. It looks like a toe.
Why does it do that? Why isn't a tendon stiff right away? I mean, it's supposed to transfer muscle power.
It has to do with the microscopic structure of the collagen fibers. At rest, the collagen fibers in a tendon or ligament are naturally crimped. They look wavy under a microscope like a relaxed accordion. When you first start pulling on the tendon, you aren't actually stretching the stiff collagen backbone itself, you are merely straightening out that wavy crimp. Straightening a wavy fiber takes almost zero force, so there is very little resistance, and the line stays flat.
But once the waves are gone...
Once you pull enough to make the fibers taut and perfectly straight, suddenly the material stiffens up dramatically, and the line on the graph shoots vertically. So the toe region is caused entirely by naturally crimped, wavy collagen fibers straightening out. It is the absolute signature of a tendon or ligament on a graph.
And before we leave viscoelasticity entirely, there is one more vital concept. You mentioned it right at the beginning. Strain rate dependence.
Yes. This is where speed comes in. Viscoelastic materials are strain rate dependent, meaning they are significantly stiffer and stronger when they are loaded quickly compared to when they are loaded slowly.
Faster equals stiffer and stronger. That is a brilliant evolutionary adaptation, isn't it? It means our ligaments protect us dynamically. If you take a slow, twisting fall on the ski slopes, the ligament is loaded slowly, meaning it behaves with less stiffness and less strength. It's more likely to simply tear mid-substance.
Exactly. But consider a high-speed violent impact, like a motorcycle crash. The ligament is loaded so incredibly fast that its strain rate dependence kicks in. It becomes incredibly stiff and incredibly strong. In fact, it often becomes stronger than the bone it's attached to. That's why high-speed trauma frequently causes avulsion fractures. The ligament pulls a solid chunk of bone off because the ligament itself refused to yield at that high speed.
That is a perfect clinical correlation. Slower load equals ligament tear. Faster load equals bony avulsion. Okay, if you only remember one thing from this viscoelastic topic, creep is constant load with growing deformation, and stress relaxation is constant length with falling stress.
Excellent summary.
And knowing how these biological materials react to time and speed perfectly sets us up for our next major topic. We are going to analyze the most important composite material in the entire human body, bone.
Bone is a remarkably fascinating, highly complex material. It gets its own dedicated focus because examiners absolutely love to test its specific properties. There are three main descriptors you must know about bone as a material.
Let's list them out and explain the mechanics.
First, as we just discussed at length, bone is viscoelastic. It contains fluid and collagen, so its behavior changes with time and the rate of loading. Second, bone is a composite material.
Meaning it's made of two different things working together.
Exactly. Like fiberglass. Bone is made of two different phases. An inorganic mineral phase, mostly hydroxyapatite crystals, which gives the bone its immense compressive strength, and an organic phase, mostly type 1 collagen, which gives the bone its tensile strength and a degree of flexibility. If you remove the collagen, the bone would shatter like a glass window. If you remove the mineral, it would bend like a rubber hose.
Viscoelastic and a composite. And the third descriptor, I know this is the big one.
The third, and by far the most frequently tested property, is that bone is anisotropic.
Anisotropic. Let's define that very carefully.
Anisotropic means that a material's mechanical properties, its strength, its stiffness, depend entirely on the direction in which you apply the load.
So it's not the same in all directions.
Not at all. Bone is highly meticulously organized by the body. The osteons, the eversion systems, and the collagen fibers all run longitudinally down the shaft of a long bone, parallel to the normal forces of gravity. Because of this incredible architectural organization, bone is much, much stronger and stiffer when you load it along its length longitudinally, like when you're standing on it, compared to when you load it across its width transversely.
So if an exam question tries to trick you by saying cortical bone is isotropic, meaning it behaves the exact same way in all directions, that is totally false. Mature bone is completely anisotropic.
Yes. However, you have to be extremely careful because the examiners have built an enormous trap hiding right here. There is one specific type of bone that is the exception to this rule.
What was the exception?
Woven bone. Woven bone is isotropic.
Wait, woven bone is isotropic. Why would one type of bone be different?
Think about when the body makes woven bone. It makes it during an emergency. Woven bone is immature, rapidly formed bone laid down during early fracture healing or in certain pathologies. The body doesn't have the time to organize the osteons. The osteoblasts are in a panic, and they lay down collagen fibers completely randomly in a disorganized, chaotic web.
A microscopic tangled mess.
Exactly. And because the fibers are pointing in every random direction equally, the material behaves the exact same way regardless of which direction you pull it. Therefore, woven bone is isotropic. It isn't until later, when the osteoclasts and osteoblasts remodel that callus according to stress lines, that it becomes highly organized anisotropic lamellar bone.
That makes profound biological sense. Woven bone is an emergency patch, so it's random, making it isotropic. I am going to state this twice for you listening because it is a brilliant exam discriminator. Woven bone is isotropic because its collagen is random. All other mature bone is anisotropic. Woven bone is isotropic because its collagen is random. All other mature bone is anisotropic.
Perfect. Now, there is one more crucial mathematical rule about bone as a material that we need to cover. It relates to bone density.
The density rule. This is the underlying math behind why osteoporosis is so dangerous, right?
Yes, it explains the catastrophic nature of the disease. The rule states that bone strength and stiffness are proportional to its density squared.
Density squared, not a one-to-one linear drop.
Exactly, it's exponential. This is why osteoporosis is so mechanically devastating. Because of the square relationship, a relatively small drop in bone mass and density results in a massive disproportionate drop in the bone's actual structural strength. If the density of a section of cancellous bone goes down by half, its strength doesn't drop by half, it goes down by a factor of 4.
I am stating this mathematical reality twice. Bone strength and stiffness are proportional to density squared. Bone strength and stiffness are proportional to density squared. Okay, let's zoom out from bone for a minute. The FRCS exam absolutely loves those. Put these in order ranking questions. We need to rank the materials we routinely use in orthopedics.
There are 2 specific rankings you must commit to memory for the exam. A ranking for stiffness, which is Young's modulus, and a completely separate ranking for ultimate tensile strength.
Let's do stiffness first. From the highest stiffness, the most rigid material, down to the lowest.
Starting from the very top, the highest stiffness, ceramic. Ceramic is the stiffest material we use. Next down are the metal alloys. The stiffest metal by far is cobalt chrome. Below that is stainless steel. Below that is titanium.
Let me pause to lock in the metals. So the metals go. Cobalt chrome is the stiffest, then stainless steel, then titanium is the least stiff of the metals.
Correct. Continuing down the list. Below titanium, we drop down to biological cortical bone. Below cortical bone are the polymers, like PMMA bone cement and high-density polyethylene. Below the polymers, a cancellous bone. And finally, at the very bottom, the lowest stiffness of all are the soft tissues, with cartilage being the least stiff.
That is a long list. Let's make sure we hit the absolute key anchors. The stiffest material overall is ceramic. The least stiff is cartilage. And among the metals, cobalt chrome is the stiffest metal, while titanium is the least stiff metal. I'm going to state the whole list twice, rapidly, for the listeners driving. Highest to lowest stiffness. Ceramic, cobalt chrome, stainless steel, titanium, cortical bone, polymers, cancellous bone, cartilage. Second time. Highest to lowest stiffness. Ceramic, cobalt chrome, stainless steel, titanium, cortical bone, polymers, cancellous bone, cartilage.
Excellent. Now we need the second ranking list. Ultimate tensile strength. Which material takes the most sheer force to pull apart? We'll go from the lowest strength, the weakest, to the highest strength, the strongest.
Lowest to highest UTS. Let's hear it.
The lowest UTS on our list is cancellous bone. It is the weakest in tension. Moving up, we have polyethylene, then PMMA bone cement, then cortical bone, then titanium, then stainless steel. And finally, at the very top, the strongest material we implant with the highest ultimate tensile strength is cobalt chrome.
Okay, lowest to highest UTS. Cancellous bone, polyethylene, PMMA, cortical bone, titanium, stainless steel, cobalt chrome. Stating it twice. Lowest to highest UTS. Cancellous bone, polyethylene, PMMA, cortical bone, titanium, stainless steel, cobalt chrome. Yeah. Now, wait a minute. Let's look at what we just laid out. I want to point out a glaring paradox here. Based on those two lists, cobalt chrome is the stiffest metal, and it is the strongest metal. It's at the top of both metallic categories.
Ah, yes.
So why on earth do we use titanium so often? If cobalt chrome is the undeniable heavyweight champion of strength and stiffness, shouldn't we use it for every single fracture plate and every single joint stem to guarantee it never breaks?
That is a phenomenal question, and answering it is the perfect bridge to our final major topic on structural mechanics. To give you the brief answer right now, titanium's lower stiffness is actually a massive biological advantage. In orthopedics, we do not always want the stiffest possible implant. In many cases, we want an implant whose stiffness closely matches the elasticity of the cortical bone it's attached to.
Because if the implant is too stiff, it steals all the mechanical stress from the bone, causing stress shielding. We will get deep into the mechanics of that in just a moment. If you only remember one thing from this topic, bone is anisotropic except for woven bone, and cobalt chrome is the strongest and stiffest metal.
Spot on.
Okay, before we move from these raw material properties to how we actually shape them in the operating room, I need to make sure these biological definitions are hard-coded. Let's do our second mid-episode recap of these concepts. I will set it up. You spike it down.
Let's go.
Viscoelasticity, creep versus stress relaxation.
Creep is constant load with growing deformation. Stress relaxation is constant length with falling stress.
Stating twice. Creep is constant load. Stress relaxation is constant length. Creep is constant load. Stress relaxation is constant length. Next is bone isotropic.
No, mature bone is anisotropic.
Yeah.
The only exception is woven bone, which is isotropic because its collagen is laid down randomly.
Stating twice. Woven bone is isotropic. Woven bone is isotropic. Next, the relationship between bone strength and density.
Bone strength and stiffness are proportional to density squared.
Stating twice. Strength proportional to density squared. Strength proportional to density squared. And finally, the extreme ends of the stiffness ranking.
Ceramic is the stiffest overall. Cartilage is the least stiff. Cobalt chrome is the stiffest metal.
Stating twice. Ceramic is stiffest. Cartilage is least stiff. Ceramic is stiffest. Cartilage is least stiff. Okay, take a deep breath. We have covered the curves, we have covered the complex biological properties, and we have ranked the raw materials. It is time for the grand finale of theory. We are shifting gears to shape beats material, structural mechanics.
We spent the entire first half of this deep dive talking about what raw materials are made of at an atomic or cellular level. But in the real world of orthopedic surgery, where we are screwing plates and hammering rods into bones, the macrogeometry of the implant, how it is physically shaped, mathematically dominates its behavior. Shape overrides material.
Prove it. How does a shape override the molecular bonds of a material? Let's start with something we use every day, a standard fracture plate.
Let's look at the bending stiffness of a rectangular plate. If you have a plate on a bone and you decide you want to make that construct stiffer to resist bending forces, you could change the raw material. You could swap a titanium plate for a cobalt chrome plate. That changes the Young's modulus, which gives you a nice linear increase in stiffness. But if you change the geometry instead, the math goes exponential. The bending stiffness of a plate is proportional to its thickness cubed.
Thickness cubed to the power of 3.
Yes. Think about what this means in the operating room. If you take a standard plate and you simply double its thickness, say from 2 millimeters thick to 4 millimeters thick, You do not merely double the stiffness. 2 cubed is 8. By doubling the thickness, you make that plate exactly 8 times stiffer.
8 times stiffer just from a tiny 2 millimeter size increase. That is mathematically dramatic.
It's the area moment of inertia, right?
Right.
Because you are moving material further away from the neutral axis of the plate, its resistance to bending skyrockets.
I'm going to say this twice because it is pure exam gold. Plate bending stiffness is proportional to thickness cubed. Plate bending stiffness is proportional to thickness cubed.
Exactly. The geometry dominates. And if you think a flat plate is dramatic, wait until you look at the math for a solid rod or a pin.
Okay, let's talk about an intramedullary nail for a femur or a Schantz pin for an external fixator.
The bending stiffness of a solid cylinder, like a rod or a pin, is proportional to its radius to the 4th power.
Radius to the 4th power? That's massive.
Yes. So imagine a high-energy trauma scenario. You are building an external fixator frame on an open tibia fracture. You feel the frame, and it's too wobbly. If you remove a 4 mm pin and replace it with a pin that has double the radius, an 8 mm pin, you haven't made it twice as stiff. You haven't even made it 8 times as stiff. 2 to the 4th power is 16. By doubling the radius, you make that pin 16 times stiffer.
16 times stiffer. This is why going up just 1 or 2 millimeters in pin size in the trauma bay completely transforms the rigidity of an entire X-fix frame. The polar moment of inertia math is simply overpowering. I am stating this twice. Rod and pin bending stiffness is proportional to radius to the 4th power. Rod and pin bending stiffness is proportional to radius to the 4th power.
That is the absolute essence of shape beats material. Now let's talk about another vital piece of hardware where geometry is king. The pedicle screw used in spinal fusion surgery.
When you are driving a pedicle screw into the spine, your biggest nightmare is pull-out. You don't want the screw backing out of the bone under load. Now, bone density obviously matters immensely, but if we look just at the design of the screw itself, what dictates its pull-out strength?
The single greatest geometric determinant of pedicle screw pull-out strength is the outer thread diameter.
The outer diameter, which is also known as the major diameter.
Correct. A screw has an inner core diameter and an outer thread diameter. The inner core diameter dictates the bending strength of the metal itself. It prevents the screw from snapping in half. But the outer threads are what bite into the surrounding cancellous bone. Fatter threads, meaning a larger outer thread diameter, equal far more purchase, more bone captured between the threads, and significantly higher resistance to pull out.
Core prevents snapping. Outer threads prevent pulling out. I'm stating this twice. The greatest determinant of pedicle screw pullout is the outer thread diameter. The greatest determinant of pedicle screw pullout is the outer thread diameter. Okay, let's move from the design of the hardware itself to how we actually arrange that hardware on the bone. We need to discuss a critical surgical concept called working length.
Working length is an absolutely essential concept, particularly when we're using a plate to bridge a comminuted fracture, a fracture with a pulverized zone of multiple fragments where we aren't trying to squeeze every little piece perfectly back together.
In a bridge plate construct, what exactly is the working length?
The working length is defined as the distance between the innermost screws on either side of the fracture gap.
Let me visualize that. If I have a long plate spanning a messy fracture, the working length is the distance between the last screw I put in the top solid fragment and the first screw I put in the bottom solid fragment. It's the central segment of the plate that is left completely unsupported, hovering over the broken bone.
Exactly. That bare, unscrewed stretch of plate is the working length. Now, this concept is where candidates routinely stumble.
I am absolutely going to push back on this because it feels completely counterintuitive. If I have a broken bone, my surgeon's instinct tells me I should lock it down as tight and as rigid as humanly possible so it doesn't move. So shouldn't I put my screws right up close to the edge of the fracture, making the working length tiny to make the construct super stiff?
Your logic makes perfect sense for primary bone healing. If you have a simple, clean transverse break and you want zero motion so the reversion canals can cross directly, yes, you compress it and make it perfectly rigid. But for a comminuted fracture treated with a bridge plate, we don't want primary healing. The biology is too damaged. We want secondary bone healing. We want a massive callus to form. And here's the catch. Bone only forms a callus if it experiences a tiny controlled amount of micromotion. It needs mechanical stimulation to trigger the chondrocytes to form cartilage, which then turns to bone.
Perrin's strain theory. The healing tissue in the gap actually needs to feel the load to know what to do.
Yes. If you put the screws right up against the edge of the fracture, the working length is tiny. The construct is incredibly stiff. Because it's so stiff, all the force of the patient walking goes straight through the metal plate, and the fracture gap feels no strain at all. No micromotion, no stimulation, no callus, no healing. And eventually, because the bone never heals to share the load, the metal plate will fail from fatigue.
It will succumb to the silent killer we talked about earlier. So what is the solution in the OR?
You intentionally increase the working length. You purposefully leave 2 or 3 empty screw holes near the fracture site. You spread those innermost screws further apart.
Spreading the screws further apart makes that unsupported section of the plate longer, and a longer section is more flexible. It wobbles a bit more.
Exactly. By increasing the working length, you make the overall construct more flexible. This controlled flexibility allows the plate to bend just slightly under load, which translates into healthy micromotion at the fracture gap. It lowers the destructive concentration of strain at the gap, allowing a robust callus to form.
Okay, that makes the underlying biology click perfectly. Spreading the screws further apart makes the plate more flexible, which provides the healthy micromotion needed to heal a bridge-plated fracture. I am stating this twice. Increasing the working length lowers strain at the fracture gap. Increasing the working length lowers strain at the fracture gap.
Beautifully done. Now let's return to the paradox you raised earlier about titanium versus cobalt chrome. We know cobalt chrome is much stronger and much stiffer. So why is titanium so frequently preferred for joint replacement stems? This brings us to the biomechanical reality of stress shielding.
Right. Why choose the weaker, more flexible metal?
Because of Wolff's law. Julius Wolff observed in the 19th century that living bone will adapt to the mechanical loads under which it is placed. If bone is heavily loaded, it remodels and gets thicker and stronger. If bone is unloaded, it assumes it is no longer needed and it resorbs. It melts away.
Use it or lose it. The ultimate efficiency of the human body.
Exactly. When you hammer a metal implant down into a femur, the metal stem and the surrounding bone now have to share the load of the patient's body weight. If you use an incredibly stiff implant, like a massive cobalt chrome stem, that stiff metal is so unyielding that it ends up carrying almost all of the body weight itself. The adjacent bone is shielded from the mechanical stress.
Stress shielding. The bone is essentially sitting there, completely unloaded, thinking it has been retired.
And because it is unloaded, Wolff's law dictates that the bone resorbs. It thins out. Over time, as the bone melts away, the implant loses its tight fit, it loosens, and the entire joint replacement fails. This is why titanium is so incredibly valuable. Titanium is a lower Young's modulus. It is less stiff than cobalt chrome. In fact, its stiffness is much closer to the natural stiffness of human cortical bone. Because the titanium stem is slightly more flexible, it shares the mechanical load much more evenly with the surrounding bone.
The bone still feels the stress of walking, so Wolff's law tells it to stay strong and thick. Titanium causes less stress shielding specifically because it is less stiff. That perfectly resolves the paradox.
It's a perfect harmony of physics and biology. There is one final definition we need to bank for the exam before we wrap up our structural mechanics. It is a pure vocabulary check. The free body diagram.
A free body diagram. What is the trick they will use on the exam for this?
The exam will try to confuse you by mixing in terms like velocity, acceleration, kinetic energy, and dynamic motion. Just remember this rule. A free body diagram is an engineering tool used purely to calculate static forces and moments.
Static, meaning perfectly at rest.
Exactly. It looks at a body like the hip joint, isolates it from the rest of the universe, and maps out the exact balance of forces acting upon it when it is at equilibrium, at rest. It only calculates static forces and moments, nothing dynamic.
Okay, if you only remember one thing from this entire structural mechanics topic, plate stiffness is thickness cubed, rod stiffness is radius to the fourth, and a longer working length lowers fracture gap strain.
That is the masterclass of structural mechanics in a single sentence.
We have covered the microscopic stress-strain curve, we have covered the time-dependent biological properties, we have ranked the materials, and we have done the structural math. It is time for the final exam. It is time for the lightning round recap.
I am ready. Let's do it.
Listeners, this is a tightly paced ping-pong dialogue to hardwire these facts into your brain. I am going to act as the tough examiner. I will ask the question, and our expert will fire back the definitive, single-sentence answer you need to pass. Fast lap, let's go. What is Young's modulus, and what does it measure?
The slope of the elastic region. It measures stiffness.
Ductile versus brittle materials.
Ductile deforms a lot before failing. Brittle snaps with almost no plastic deformation.
Toughness versus resilience.
Toughness is the total area under the curve. Resilience is the elastic region area only.
What is the endurance limit?
The specific stress threshold below which a material never fails by fatigue.
Creep versus stress relaxation.
Creep is constant load with growing strain. Stress relaxation is constant length with falling stress.
What does the toe region on a graph signify?
A tendon or ligament. It represents the naturally crimped collagen straightening out.
Is bone isotropic?
No. Mature bone is highly anisotropic. Only emergency woven bone is isotropic.
Plate stiffness and rod stiffness are mathematically proportional to what?
Plate stiffness is proportional to thickness cubed. Rod stiffness is proportional to radius to the fourth.
What is the best way to reduce fracture gap strain in a commemorated bridge plate?
Increase the working length by leaving empty screw holes near the fracture.
Pedicle screw pullout. What is the biggest geometric factor?
The outer thread diameter.
Incredible. And that brings us to the true synthesis of everything we've discussed today. You, the listener, now hold the master keys to the invisible war zone. The stress-strain curve reads out the raw material properties: stiffness, strength, ductility, and toughness. Viscoelasticity explains how time and speed bend the rules for living biological tissues. And structural mechanics proves that geometry absolutely overrides material, thickness cubed, and radius to the fourth.
You now have the intellectual framework to look at any X-ray, any implant, and any bone, not just as a static piece of architecture, but as a living, dynamic system of forces.
But before we sign off, I want to leave you with a final, provocative thought, something to mull over on your drive that builds entirely on what we've just learned. Today, in modern orthopedics, we completely rely on static implants. We drill a static titanium plate onto a bone, we adjust the working length manually, and then we sew the patient up and cross our fingers, hoping that Wolff's Law and the micromotion handle the biology perfectly over the next 6 months.
Right, we set the initial mechanical parameters, but then we passively let nature react to our static math.
Right, but what happens to structural mechanics when smart implants arrive? Imagine a titanium fracture plate equipped with internal microsensors, an implant that actively reads its own real-time stress strain curve and transmits that data to an app on your phone. What if that implant could autonomously tighten or loosen its own internal screws, actively and dynamically adjusting its own working length day by day as the callus forms and the bone's modulus changes?
We would move entirely from passively hoping for the right strain to actively and continuously orchestrating it. The shape wouldn't just beat the material, the shape would adapt in real time to the biology.
The invisible battle of forces wouldn't just be something we can visualize, it would be something we can actively control from the outside. It is a fascinating future to think about as you prepare to enter this field.
It certainly is the next frontier of biomechanics.
Thank you for joining us on this deep dive into biomechanics and structural mechanics. We hope you found these master keys helpful, and we wish you the absolute best of luck applying these mechanics in the OR, and most importantly, on your FRCS exam. Stay curious.
And keep visualizing the forces. Until next time.